Rick already said we are talking about some projection of occurrence of the extreme dry wet years by using stationary and non-stationary statistics. In the region is Europe. The work was done in collaboration with a few colleagues. Most of them are from JRC. They are listed here. In particular, there is here Andreas Ster from Royal Meteorological Institute in Netherlands. So I will start by giving some definition of what we mean for extreme weather event from statistical point of view. Then I will show the dataset, the ENSEMBLE dataset that we have used for this study, and in particular the bias correction that some colleagues from here have done with the output of the ENSEMBLE model data. Then I will give a few definitions of the main used index for detection of dry and wet period. One of the most famous is the Standardized Precipitation Index, and then the definition of the relative Standardized Precipitation Index used for projection of dry and wet extreme periods under climate change. And then by using some non-stationary statistics, we define this new index called Standardized Non-Stationary Precipitation Index. As a result, we will start first by showing some empirical prediction. We will just calculate the probability difference by using simple empirical method. And then the final result will focus on understand if today extreme wet or dry period will continue to be classified as an extreme in the future. This is very important. It was one of the most important part of the IPCC report on extreme. And then we will have some discussion, conclusion, and remarks. So one of the most famous definition of extreme from statistical point of view was given by the father of extreme value statistics, which is Gumbel. Here is reported in France, and so he said that there is always a probability that an extreme event can occur, even under stationary conditions. So we don't need climate change to have an extreme event. And even under stationary climate, we can have extreme event. And from statistical point of view, an event is called extreme if it is from the tails of the climatological distribution, and for example can occur just only 5% or less of the time. In the left panel we have here the normal distribution. We see that the cold extremes are marked in green and the hot extremes are marked in red, and just are the temperature values on the tails of this distribution. Under climate change, under non-stationary climate, the distribution are at least shifting, and we can see that in the right panel of this figure that what was called extreme today by shifting of the distribution, what was extreme can be normal in the future. So the probability of occurrence of an extreme event will increase, and what was extreme today can become the norm under non-stationary climate. In this study, as I said already, we will use the ENSEMBLE dataset. The ENSEMBLE dataset is composed by 20 high resolution regional climate models, And these climate models are driven by 8 different GCM, global climate models, forced with the A1B emission scenario. The time steps of this model is 6 hours, and the period is between 1961 and 2100. Some models stop in 2098. The spatial domain is in Europe, and the spatial resolution is 0.22 degrees. In this study, we don't use all the 20 models, but just 5 of these models reported here. We have here a table with the institute developing the model, the regional climate model used, and then the driving global climate model. We use just only these 5 because they were bias corrected by Dozy et al. In 2012 by using the EOBS data. EOBS are the analysis data. So Dozy et al. Have calculated a transformation function between large scale and the scale of the EOBS data, and have bias corrected this data in the present, and then by using the same transformation they have corrected the precipitation data in the future. We will calculate a few indexes from this data, and the first one is the standardized precipitation index (SPI). The computation of the SPI is a 3-stage process. First of all, a parametric statistical distribution is fitted to the observed precipitation records. In this figure here, we have an example of a station in Malaga, is one grid point of our model, and in the y-axis we have a probability value. In the x-axis we have yearly precipitation amount, and we see that the gray point here are the yearly precipitation amount from the model outputs, and the black line is the cumulative distribution function fitted to the data by using a gamma distribution. The second step of the calculation of the SPI is that non-exceedance probability of precipitation observation is computed related to the parametric distribution. So what we do in the second step is to take a precipitation value. Here in the x-axis is 248 millimeter, and we transform these values in a probability value. In this case is 0.022, and then we use these probability values for the last step. The third step is that the non-exceedance probability is transformed to the standard normal variable. So we use on a standard normal distribution reported here on the right. We take the value, the probability value for corresponding to these precipitation values, and we move on the standard normal distribution. The SPI value associated with this distribution is equal to -2. And this is the values of the SPI. McKee et al. Have defined a classification of the value of the SPI. The classification is reported in this table. As we can see, the SPI equal to -2 is an extreme dry event. The SPI greater than 2 is an extreme wet. And these are the two levers that we will use in this study. So in this study, we will just consider only extreme wet and extreme dry period, and we will see if events that are considered extreme today in the present climate will move in other level of the McKee classification. So if an extreme dry season or year will become moderate or normal we can detect this by using the differences in probability value. So by using the SPI, we have here a time series. We want to use the SPI to detect change in probability. So we have to modify this index and to use the relative SPI that is defined in this panel. First of all, if we are on the present, we take the gray point on this plot on the top of the figure, and we consider just the gray point, which are precipitation model data between 1971 and 2000, and we model with the SPI this data by using the gamma distribution as explained in the previous slide. Then for the definition of the SPI, we consider 30 years of the last period in the future, the orange points in this panel, and we model with the gamma distribution this point. We fit with the gamma distribution this observational model outputs, and we get this CDF curve reported here. So the values of the relative SPI is calculated as follows. If we take the precipitation, the yearly accumulation of precipitation is not written very well here, but it's the values that we have considered before is 248 millimeter per year. We can move from present to the future by using the brown CDF, and we can calculate the SPI for the future. SPI in this case is minus 0.9. So we see that if we go back to the table that I have reported before, we see that a present value of 248 millimeter of precipitation with a corresponding SPI of minus 2 as in the future SPI values equal to minus 0.9, meaning that what was extreme in the present is now becoming normal, is in the normal band in the future. And for this study, we do not consider the SPI value for estimation of occurrence of extreme dry or wet period in the future, but we will consider the differences between the probability values between future and present. In this case, we see that in the present we had the probability of 0.022, and in the future we have a probability of occurrence of the same event, which is almost close to 0.2, so it's 10 times greater than the present. These differences will tell us the probability of occurrence of an extreme dry or wet period. But we have used the relative SPI, but we thought that if we model just 30 years in the present and 30 years in the future, we maybe can have some wrong estimation of the trend of the data in the time series. If we have a linear trend, is okay. We can even consider 30 years in the present and the future, and we should obtain the same result as in the case we use the entire time series. But if we have some nonlinear trend, we can have some overestimation or underestimation of our results. So, in fact, in this case, which is a linear trend, but if we consider then the whole time series, the orange point between the period 1971 and 2100, we see that by estimating just a simple linear trend, we have different results in the trend that could be sometimes significant, sometimes not significant with respect to the trend between two sub periods. So we thought that was better to model the entire time series by using non-stationary gamma distribution and by defining the non-stationary standardized precipitation index. The non-stationary standardized precipitation index is defined as the relative SPI, but with just one difference on the first stage in the calculation, where we use a non-stationary gamma distribution to transform the precipitation time series into corresponding time series of probability values. The fitting with a non-stationary model is done with a generalized linear model and is fitted here by maximum likelihood. The fitting is done by linearly varying the scale parameter of the gamma distribution. So if we consider this gamma variable, we have the scale parameter depending by time, and the A is the shape parameter. As we know, the gamma distribution is a two-parameter distribution, and the scale parameter is related to the location parameter. In fact, the scale is given by a relation between the location and shape parameter, and the variation through time of the scale parameter is given by a linear trend in the location parameter reported here. And so variation through time are modeled by means of a gamma distribution with different means and variables, but a common shape. This is an important point because by using this non-stationary index, we are fixing the shape in the present, constant between the present and the future period. By using the relative SPI, we will see that we are not fixing the shape parameter as constant between present and future because we are doing just two different fittings. And before we show the result obtained with the precipitation index, we have just empirically estimated the differences between future and current climate of just something that empirically can be considered as a dry extreme, in this case for annual precipitation amount. We have taken the second percentile for each model output, and the result of the difference between the second percentile of the future period and the present period, we stop in 2098 because, as I said already, some models stop at 2098, so the last 30-year period are reported here just between 2069 and 2098. And the differences between the second percentile for each model are reported here. And the color scale here is the precipitation change in 100 year in millimeter. And we see that the red color scale represents the drier region, the point where we have a drier climate, and the blue color scale represents the region where we will have wetter climate. We see that there is some model predicting drier year in the future almost everywhere in Europe, whereas there are other models like the DMI, ECAM5 that predict just very small area becoming drier at yearly scale. So if we take the ensemble of these 5 models, we can proceed in different way to calculate empirically the changing of yearly precipitation amount. If we just take the second percentile for the full 5 model ensemble, we get this panel here in the bottom and called A, where we see that the drier area in the southern Europe is very extended, and it seems to follow more or less the two driest model. This is because when we calculate the second percentile of a 5 model ensemble, we sort the data, and is the driest model which is dominating in the calculation. Whereas if we take just the median of this second percentile of the ensemble, we see that in the Central Europe we get a completely opposite result. We have that region where we projected drier here are not drier in the future, but are even wetter in the future. So by changing the method of calculation, we can get different results. And this is the case of the different standardized precipitation index that we have used for this study. In fact, if we use the SPI probability difference reported here, we see that the SPI follow the A case of the previous slide, where we just have calculated the empirically changing of precipitation amount. It seems that just the dry area in the future is very extended. The white area here represents the area where a significant climate change was a non-significant climate change was detected. We did this estimation by using a Kolmogorov-Smirnov test between present and future data. If we calculate the non-stationary precipitation index, we see that we get different results. Similar results are obtained for the non-significant area where we don't get any significant change in precipitation, yearly precipitation amount. And this is an important result because in the case of the standardized and non-stationary precipitation index, this white area was obtained by using a different statistical test, a likelihood ratio test. So by using different method, we get more or less the same result. By looking to the change in the probability change of occurrence of wet and dry here, we see that in the northern Europe, where in region where SPI was predicting drier here, with the SnsPI we get wetter here, or close to zero, not very big change. So what we thought was that maybe the SPI is just a two parameters. So the gamma distribution used in the calculation of the SPI is just a two parameter distribution, and maybe if we use more parameters, we are able to better model this region. And we have used a different SPI index called SPI-GV index. That is the same of the SPI-GV is the same of the SPI, with the only difference that the data are modeled with the GV distribution. The GV distribution is a generalized extreme value distribution. I will not go on the details of the distribution, but what is important is that it is a three parameters distribution. So it is defined by using location, scale, and shape parameter. And we see that by calculating the SPI, by fitting data with the GV distribution, we get the same result more or less as the SPI. The drier areas in the Central Europe are still drier, also by using this SPI GEV. So we talk again, and that the SPI is defined for two periods, one in the present. So the relative SPI is defined for two periods, one in the present and one in the future, and the shape parameter between present and future is not constant as in the standardized stationary precipitation index. It's free to change between present and future, and the same is for the SPI GV. So what we did, we have taken the three-parameter distribution, we have fitted the GV, the present data, by calculating the location, scale, and shape parameter, and then we fit data for the future by fixing the shape of the future equal to the shape calculated for the present. In this way, we can have this SPI GVC constant, which is the fitting of is calculated by fixing as constant the shape parameter of the GV distribution. So we see that we have not so big differences, but what is important is also that we have tested that the shape parameter is not significantly changed. What is significantly changed under non-stationary climate is the location and the scale parameter. So by using the standardized non-stationary precipitation index, we have tried to give some projection of the extreme dry, a wet year and season, and we see that in 50 years at yearly scale, we will have drier. The southern Europe is becoming drier, and the northern Europe is becoming wetter. So the extreme wet year will become more wet, and the extreme dry year in the southern Europe will become drier. The same is detected in 100 years of climate change, but with the magnitude of occurrence of extreme dry wet period higher than in the previous 50 years. At seasonal scale, we see that some in the next 50 years in the southern Europe are becoming drier, and in 100 years we have the same more extended areas becoming drier in the summer in the southern Europe, whereas for the extreme wet, just the northern Europe is becoming the extreme wet are becoming wetter in the northern Europe. In winter, we see that the winter season are becoming wetter almost in Central and in Northern Europe. Just small areas in Mediterranean country are becoming drier. We will have drier winter just in this Mediterranean area. And in 100 years, the magnitude of this probability of occurrence is higher than in the present year, but the partners of changing are more or less the same. So we have investigated change in probability of occurrence of extreme dry, wet years and season by using precipitation data simulated in the ENSEMBLE project for the 21st century, and the probability change has been estimated with a few indexes, but in particular with this standardized non-stationary precipitation index, and the SnsPI is found to be more robust in describing precipitation change as it uses data over the whole period rather than from two sub-periods only as for the SPI. Then, under the A1B climate change scenario, the probability of having an extreme precipitation season is increasing overall of Europe dry areas are become drier and wet areas are become wetter. Dry season are becoming drier and wet season are becoming wetter. Throughout the simulation period, the spatial partner of change are the same. And finally, change are mainly associated with the shifting and widening of the location and scale parameter, while the shape parameter does not change significantly, neither for annual nor for seasonal precipitation amounts. Here I report some references. In particular, this work is already published in Journal of Geophysical Research. And thank you.
Okay, thank you very much, Simone. Very nice talk. You're right on time as well. And it's very interesting to see that you're showing the results so clearly, what the effects are of using different distributions as well. I can now take some questions from the listeners, and you can either ask directly.
Yes, for sure.
Yeah. Or you can also use the chat function if you are not unable to have a microphone. So please,
no,
question.
For me, it's better just to listen to the question, and I will also use the chat. Okay.
Yes. Okay. So questions.
Okay. Okay. Okay.
I don't see any questions at the moment. Maybe you were very clear in your talks. Maybe there are not so many questions. But I can just, I wasn't sure if I got it in the beginning. Oh, sorry, we have a question here. Yes?
Hello?
Hello?
Simone.
Yes.
Thank you very much for your webinar. It was very interesting, and I think that my students are very happy to follow these results, interesting, and we have in future to discuss about this. Thank you again. Hello.
Thank you. So, Frederick.
Yeah, so just a question there, whether you're using the, is it the 1 monthly SPI in this study?
No, I've used just 3 months SPI and yearly precipitation amount. I didn't use it. Yeah. Yeah.
What about the annual precipitation amount all the time you're showing?
The annual, yes.
Mm.
I've used the annual and the seasonal precipitation amount.
Okay.
Yeah, because at monthly scale, okay, just in climate maybe it's not so important to use monthly scale. But the problem with monthly scale are the zero in the precipitation. If you use monthly scale, okay, I think the SPI is good too, but sometimes you have, if you use 30 years of data and then you have 10% of zero in your time series, could be a problem. So I since we are giving some estimation for climate, so I prefer just to skip the monthly scale using just 3 months and
yes.
Months.
Yeah, I completely agree.
Yeah.
Do we have any more questions? I just have another question here as well, Simone. So
yeah.
This is also in line with what we've seen on terms of looking only at the precipitation itself. So what do you think is the advantage of using an index like the standard SPI to get a more, what is the advantages apart from just looking at the precipitation itself?
What is the advantage of, in general, of the SPI index in modeling precipitation, or between stationary and non-stationary? I didn't understand if you just want to are you talking about the advantages of use the standardized precipitation index?
Yes, exactly.
Yeah, I think what is good in this kind of indicators is that you can standardize precipitation through time and space. So, because we have, for example, in Europe, the variability of precipitation between northern and southern Europe is different. But in this way, by using some standardized index, you can just transform to probability scale, and you can compare wet region with dry region more or less, okay, in the same scale, because it's the scale of the standard normal distribution. In this case, I have preferred to work with the probability scale between 0 and 1.
But of course, it's going to be different as well to the sensitivity to the drought as well for different regions.
Yeah, there is some sensitivity, but if you standardize, finally, you are just evaluating with respect to the variability of the precipitation in that region.
Yeah.
I think, yeah.
I have another question there as well. You were looking now at sort of the median of the models, but can you see, if you compare the change into the future with the variability between the models themselves, yeah, how does that compare? I mean, what I'm asking is more or less if there is a large change difference between the models themselves, then you can see the actual change.
I cannot hear you very well. Can you repeat, please?
Yes, so it's whether the difference between the models is bigger than what you can see in terms of the change in the future.
Ah, okay. So if you mean the bias of the ensemble is influencing maybe more than the, yeah, we have estimated the ensemble bias, and it is very small with respect to the change of the future, even because these 5 models are bias corrected. So what we did, we have just reduced the bias of the ensemble, because are all related to the EOBS data. So finally, I think the bias correction is a good method, maybe just to reduce this bias of the ensemble. And finally, it doesn't give any, it can give any addiction to the climate change result, because finally what we see in many bias correction methods, they do not, so the trend in precipitation will remain more or less the same. What is reduced is the bias, is the spread of the ensemble model.
Yes.
So I think, yeah, yes, sorry.
That spread is mostly due to model biases themselves, so it's sort of a, it's not a real spread, it's more of a model error spread.
Exactly. Yeah.
Okay, thank you very much, Simone. Do we have any more questions? Do you have any more comments? Okay, otherwise, thanks, Simone, very much for the very interesting talk.
Thank you.
And I will put this shortly up on YouTube as well for you who see you again.
Thank you. Thank you.
And so thank you again.
Thank you again. Bye.
Bye.
Bye. Bye.